Hello everyone and welcome to this video. Today we're gonna discuss the double integrals in the polar form. So first of all we have a picture here um, on the polar coordinates and how we convert from regular coordinates to the polar coordinates. And as you can see we have two functions here. We have first r equals g1 of theta, and then we have r equals g2 of theta, and this is the other function here. And so these functions bound the region shaded in the orange. As you can see, these functions bound this region, which is g1 of theta and g2 of theta. And then we have also theta starts at alpha, so our first angle is alpha, and our second angle is beta, so theta equals beta. And so here there are also some changes which are delta r's. Okay, so we have each difference here is a delta r, which is a very small change in the radius. And so as you can see, here are the conditions for our region R. It lies between the two functions g1 of theta and g2 of theta, and also they are between the angles theta equals alpha and theta equals beta. And as you can see, we have a different region, which is region Q. And region Q is between r equals a and r equals 0. And it's also between theta and alpha. So this is our region. Basically the region Q is this outer region that includes region R. And so this is the outer region, is our region Q. And these are all definitions. As you can see, also we have here the very small change in area, which is delta AK, and that's the very small change in area. We have also the change in radius here. So the change in area is basically delta AK is basically gonna be delta R times delta theta. Okay, and this is gonna be given at the point RK and theta k. So each point has an index which is k. So k is an index. So for example, we're gonna say that this area has an index of 10. K equals 10. Now we don't know if it's 10, it can be any number, but this number is unique for each square, and that's why we call it k. It can be any number. We don't know what is the number for this specific square, so here we're gonna say it's k. And that's basically our very small area, and that's how we define it. And then and this is important because we're gonna use it now in our definition, and because we're gonna now integrate in the polar coordinate, and so because sometimes it's easier to integrate in the polar coordinate since some functions are, become simpler. So for example, x squared plus y squared equals, for example, 2. Now this can be written in polar as just basically r squared equal 2, or r equals square root of 2, and this makes it simpler for us to graph and also to try to integrate in general. I'm going to show you why, and we're going to show you how to integrate this when we convert from regular coordinates to polar coordinates. And so as you can see here, now this is our way of finding delta A, and actually delta AK should also include RK. Okay, so the formula is actually RK times delta R times delta theta, and now I'm gonna explain why exactly. Now, so going back here, now we're gonna define our very infinitesimally small area component delta AK. So we're gonna define that, and so we have here basically this sector. This is a small sector, okay, and of that area. So let's say now we have delta AK. Okay, so we want to find the area of this small sector. Okay, now how can we do that? So first we need to define a point. We call it RK. Now this is the point at the middle of our area. So at the middle of our area that we want to define, this point resides there. And so if you go at the very end of that area, we can find that we have RK plus delta R over 2. Okay, delta R is the change in the radius. Delta R is the change in the radius as we go up this way. This is delta R. This is the change in radius. It goes this way. Okay, but it's divided by 2 because this point is in the middle of the area. So it is in the middle of this area, and that's why we divide by 2. And then if we want to go to the lower end of this area, let me draw it on the side here. So this is our area, basically our very small part of area. Okay, so and we have here delta R. We have also here this point, we have RK. Okay, we have also RK plus delta R over 2, since this is the midpoint, and then this is here, we would say it's RK minus delta R over 2. So this has a less value, a lower value than RK. And also we have here, as you can see, delta theta, and delta theta is basically the angle. And so if we extend this line like this, as you can see, we're gonna get here an angle. So this is theta. Okay, so and now the area, if we want to define this area, we can say that it is basically an area of any sector. Okay, if we have a sector of a circle, so let's say this is a circle and this is a sector, the area of any circle, any sector is just A equals R theta, where theta is just the angle of the sector and R is the length of one of the sides of this area. So we want to find this area, the area of this sector. So this area. So we'll need R and we'll need theta. So now what is R in our case? Now R, we are not using the whole R of the sector. No, we are using just delta R. Or we want to find delta R. We want to find this area. So I know, how can we do this? We can basically we can imagine that we have two sectors, okay? Or that we have two circles. So let's say we have a bigger circle like this, and we have a smaller circle inside it, and our little sector that we have here, okay? So let's say this is an extension, okay? This is an extension of what you have. So this sector is what we have here, okay? Let me just draw this a little bit better, okay? In order to see this, okay? And so here we have this sector, okay? And we want to find this area. Now, in order to find it in our terms that we used here, okay, in which we define the area of a sector, we can basically say that delta A, which is we are trying to find, this is what we are trying to find. So delta A is basically area of large circle minus area of small circle. And that's our area. That's our little difference in area. So it's the area of the large circle minus the area of the small circle. Now what are the areas for the large circle and the small circle? So we can find it. So as you can see, this is basically, so it's not a circle, it's a sector. So the area of the large sector minus the area of the small sector. Okay. And then, so delta AK is this. Now, this, we're gonna show you how this leads to a formula that we can use. Now, let me erase this. So let me erase this and show you exactly what do I mean by this. Now we're gonna try to use our definitions that we defined for that R and also the points and the endpoints. And now you could have asked, why did I find this point and this point? Now I'll tell you why. Now these points are gonna be used in our formula, which is delta AK. Okay, so now let's try to do this. So we said delta AK equals area of large sector minus area of a small sector. Okay, and now what is the area of the large sector? So it's basically this point. This is the R here. Okay, so this is R for our large sector, and also we have here delta theta. And so the area of the large sector is RK plus delta R over 2 times delta theta. Now this is the area of the large sector. Now if we want to find the area of the smallest sector, it's RK minus delta R over 2 delta theta. So now if we want to simplify this, so we're gonna have delta AK equals RK delta theta plus delta R delta theta over 2 minus RK delta theta, and then plus delta R delta theta over 2. And now these two will cancel, and we're gonna have basically the formula delta AK equals, and yes, so this should be the way we do it. So it's RK plus and minus, and we should get a formula which says delta R delta theta. Okay, but we are missing an RK, and I want to know why. Okay, so basically we do have RK here, and we do have delta R plus 2, so this is our bigger radius. Okay, so this is our bigger radius, and we do have delta theta. Now this is an area, this is basically the formula for a sector's area. Now we also have delta R minus delta R over 2. This is the radius for the smaller sector multiplied by the theta, the angle. And now if we substitute, we get one positive value and one negative value. And well, it's interesting. This leads me just to delta R delta theta. Now this would be the, you know, the most the most obvious formula, I would say. Yeah, and so okay, so if he's maybe talking about the whole area of the sector is gonna be just this. We're gonna multiply delta AK by RK. So delta AK is gonna equal to RK delta R over delta theta. So maybe he's talking about the smaller area here, but here he's talking about the whole sector, because when we multiply this by the whole RK, we're gonna get basically this angle. So this is the formula. Okay, so it leads to this formula, RK times delta R delta theta. Okay, and RK is basically the radius from the origin up to the midpoint of our area. And it's a bit interesting, how did this turn out to be? It's interesting. Maybe I'm missing something. Rk plus delta r. Okay, we do have Rk, regular Rk times theta. Okay, delta theta. Well, it's interesting, but basically this is the formula, and we're gonna try to find out now why is that. Okay, so this is the formula, and so okay, so let's solve some examples, or let's see. This is an example of yeah, so this is an example. See, so we have 2 and okay, so let's look at this first part. Okay, so first we have y equals square root of 2. This is our line. So now this line is given and this area is given, and maybe he would ask us to find the area of this region. Okay, and we also have this formula, so x squared plus y squared equals 4. Okay, so this is basically the outer bound of the region. And then we have here a point, root 2, and we have also here the intersection with the y-axis is at 2. And then yeah, and then if we draw a line to try to find the area of this region, if we draw a line, we're gonna draw a line from the origin cutting through the area. And now there are 2 bonds for this line. So the line, we're gonna consider two major points for a line that's cutting through the area. So the first major point is the entry line, which is so it is the entry point. And then we have also the exit point, or the leaving point, so let's say exit point. And these are important points for each line that we cut through. And so if we go here, we can see some important also information, which are the angle. So we do have the angle here, which is the angle at which we start with our line. Okay, and basically this line is y equals x, at which these 2 graphs intersect. So if you're not sure why, so x squared plus y squared equals to 4, and then we do have also y equals root 2, and then when we put root 2 here, we're gonna get, when we substitute y equals root 2, we're gonna get x squared plus 2 equals 4, or x equals, we get plus minus 2. So there are 2 intersections, and so actually it's root. So root 2 plus minus 2, and that's why we get here the point. As you can see, if you go here, we get the point root 2, and that just basically makes sense. So so let's just remove this. Then it's our entry point. Okay, and then the line will extend through the angle. It will start from the angle pi over 4. Okay, and how did we get pi over 4? It's basically, we first need to find the point, this point. So we said this point is root 2. Okay, and this is because of our substitution. Now y is root 2, x is then also root 2. There is another negative value of x, but we won't use it, we use this. And then now how we find the angle? We find the angle. It's basically tan theta equals y over x, and y is root 2, tan theta is root 2 over x, which is root 2, which is tan theta of 1. And when do we get a value of tan theta? that gives us 1. So a theta value of 45 degrees or pi over 4 radians will give us a value of for tan theta of 1. So if we take tan inverse of 1, it will give us 45 degrees or radians pi over 4 radians. And that's exactly from where we got pi over 4. Now, for pi over 2, that's basically obvious. It stops at the at the y-axis, and the y-axis is basically pi over 2. So our line is gonna cross this area. It's gonna go from pi over 4 up to pi over 2. Now we found the angle, but now we need also to find, in polar coordinates, the most important coordinates, or the coordinates that we use in polar, are the radius and the angle. So now we found the radius, the angle theta. Now we need to find the radius r. And now this could be a bit tricky, depending on the graph. So now we do have this graph in regular coordinates, not polar coordinates, and we want to find it, to convert these coordinates, the polar coordinates, into r and theta. Now we found the thetas, okay? Now we want to find the r's. Now we do know. Now this show you how would I do this. So now I do know that I do have two equations. I do have equation 1. Just zoom in. So I do have equation 1, which is x squared plus y squared equals to 4. I do have also another equation, which is y equals square root of 2. Now, we know also that in polar, y equals sine theta and x equals cosine theta, or r cosine theta, r sine theta, r cosine theta. So these are the conversions from polar to the regular coordinates, okay? Cartesian coordinates, from Cartesian coordinates to polar coordinates, and vice versa. So these are the ways we can convert. And so we can basically say that, and also we have x squared plus y squared will equal to r. This is also another conversion. R squared is also another conversion. So this can be converted to r squared equals 4, which is basically saying that r equal to 2. Yes, r equal to 2. We can have minus 2, but we'll use the positive value for our polar coordinates. Now, r sine theta equals root 2 can also be converted. So this is y. So we said y is r sine theta, and so we can say r sine theta equals root 2, and therefore r equals root 2 cosecant theta. And now we have r, so we can say r is bigger than or equal to, or sorry, yes, it's bigger than or equal to, but still less than or equal root 2 cosecant theta. Sorry, that's the opposite. So r is bigger than or equal root 2 cosecant theta. Okay, and that's because y is, if we draw our line again, y equals root 2 is the lower limit, and so it's gonna be the lower limit, and the upper limit is gonna be just r squared equals 4 or r equals 2. And now we do have the range for r. We do have the range for theta. We said it's bigger than pi over 4 but smaller than pi over 2. And now basically we can integrate in order to find the area. Now in Cartesian coordinates, we say that the area, or we know that the area is just the double integral over the domain of the area, then by dA. So this is the way we find the area. Now we will need to convert this dA into the polar coordinate system, and we're gonna show you exactly how. And that's basically here, as you can see, this is our last part for this section. So as you can see here, it enters at r equals root 2 cosecant theta, as we said, and then it leaves at r equals 2. Okay, and for the angle we decide the angle, and this is exactly what we did. So basically we need to find the limits of integration in the polar coordinates. And now after we found the limit of integration. Now this is another example of finding the limits of integration, and it's important because the limits of integration are basically finding them is one of the most important things that you will do, or the important thing, the most important thing that you will do in integrating, because if you got it wrong, then you get the area wrong, and that's not something that you want to have. And so here we do have the angles given. So we do have the outer radius. So if we draw our line here, we already have the line. Okay, so we already have the line. So the line here, our arbitrary line, leaves at r equals 1 plus cosine theta. Okay, so it leaves at r equals 1 plus cosine theta, and it enters at r equals 1, which is basically a circle here, and the outer one is they call it it's the heart-shaped graph. They call it the cardioid. Yeah, they call it cardioid since it looks like a heart, so the cardio, or yeah, I misspelled cardio also. Cardioid. Yeah, I think it's that. But it's that's the name of the graph. It's any graph which you have r equals a plus minus b cosine theta, or r equals a plus minus b sine theta. And these are the graphs for cardioids, and this is the cardioid, and we have also a circle. And also, yeah, so here we can say that it enters at r equals 1, and also since this is our area, we are not considering any other area, so we can say that theta, our starting theta, starts from pi equals negative pi over 2, theta equals negative pi over 2, going up to theta equals pi over 2. Okay, and these are our thetas. And so we found the limits of integration. Now we can use this information in order to find the area of any shape, and also the volume, and we're going to discuss how we're going to do that exactly. So now we have an example. He wants us to find the limits of integration for integrating f r theta over the region R that lies inside the cardioid. Yes, it's a cardioid, as I said. R equals 1 plus cosine theta, and the circle r equals 1, which is basically this. It's basically this. So we already found it, so this example is already solved. So, but how would I do it if I did not know the solution? I would basically first take a screenshot of this, go to my board, and try to solve this. So that's the first thing I will do. So let's go here, then done. Okay, so the first graph is a circle with radius r equals 1. Okay, so this is a circle with a radius of r equals 1, and then we're gonna draw also cardioid, which is gonna look something like this. Okay, this is our cardioid. Now this is just an approximation. Okay, and this is so 1 plus cosine theta, and this is r equals 1. Now if we want this region, okay, so we want the area that lies, he said, inside the cardioid. Okay, so this is our cardioid, so the area inside the cardioid and outside the circle. Okay, so it's not included in the circle, which is basically this area that we shaded. Okay, and then we're gonna draw a line from the origin, and we're gonna identify the outer the outer the outer bound. So the outer bound is just 1 plus cosine theta, and the inner bound, which is r equals 1. Now for theta can go from, as you can see here, minus pi over 2 to pi over 2. And with that we found our limits of integrations. So the lower limit is 1, the upper limit is 1 plus cosine theta. And for theta, the upper limit is, or the lower limit is minus pi over 2, and the upper limit is pi over 2. Now these are our limits of integration, and we solved part A. Now going to part B. For part B, he wants us to find the R limits of integration. Okay, we already found the R limits of integration. Now, he wants us, for part 3, to find the theta limits and the rays, okay, from the origins that intersect R, which run from minus pi over 2 to pi over 2 in the integral. Okay, so he wants to find the integral, wants us to find the integral, and the integral basically is gonna be A equals double integral of d dA. Now dA in the polar coordinate is just r dr d theta. Okay, now this is our dA, and this is basically the definition of the area component in integration. So we're gonna basically say, and also if we have a function that we want to integrate, we're gonna add that, so which is a function of r theta, so dA, and so the area will be basically f of r theta r dr d theta. So, and for first we're gonna add the limits for r, which is 1 to 1 plus cosine theta, and then the limits for theta, which are minus pi over 2 to pi over 2. That's basically the area, or the integral. Is this an area or a volume? Well, it could be an area, it could be a volume, but yeah, basically this could be a volume. But let's just leave it as an integral, okay? And let's just not say that this is an area or volume. Let's just leave it as it is, as an integral. And then it's gonna tell us exactly whether we need to find an area or a volume. And so, okay, so that's what we are talking about. This is the area in polar coordinates. The area of a closed and bounded region R in the polar coordinates is just this formula. A equals the integral of R dA, and given that dA is equal to r dr d theta, so A is just the integral over the region of r dr d theta, and that's our formula that we are going to use. And now this is another example. You can use many examples. Now we have this function r equals square root of 4 cosine 2 theta, which is basically, they call it, what do they call this? It's like a flower shape, like a leaf, something like this, maybe a leaf, or anyways. So there is no entry point. The entry point is just r equals 0. Okay, so if we had, for example, a circle here with r equals 1, then our entry point is gonna be 1, since the area is gonna be here only. But now we don't have that, so we're just gonna say that the entry area or the entry point is just r equals 0. And now for the theta, so theta is just can be from 0, can go from 0 up to the upper limit of our area, which is pi over 4. Okay, now how do you get pi over 4? Well, basically we can see that it's pi over 4, okay, if we graph it. But my guess is that if we substitute the square root of 4 cosine of 2 times pi over 4 will give us the square root of 4 cosine of pi over 2. Now cosine of pi over 2 is just 0, so r equals 0. Okay, and this is basically when r returns to its value. So r first when theta is pi over 2 minus pi over 4, the r is also 0, but the r also increases with the angle. It does increase until it reaches pi over 4 and comes back to 0. Now if we go and continue, okay, if we continue with theta, we're gonna get a negative value for r. Okay, we should get a negative value for r, or basically we should not get any value since we have square root, and cosine of anything, cosine of 2 theta, when theta is bigger than pi over 4, is going to give a negative value, which is not possible in the square root, so we are not going to get anything. So if we continue even, we're not going to get anything, any value. The function is not defined. That's why we need to make sure we are integrating in a region that's in which the function is defined, and that's why we said pi over 4 and not, for example, pi over 2, because for values between pi over 4 and pi over 2, this function is not defined, since cosine 2 theta in this region is also negative. And that's basically that. We need to make sure also that the bounds are positive and are defined in our region. And that's basically our bounds. So yeah, so r is bigger than or equal 0, smaller than or equal square root of 4 cosine of 2 theta. So this is basically r squared equals 4 2 theta. Okay, yeah, so r squared equals 4. So actually no, for this function it is defined, but for our function, this little function is not defined. Anyways, we do stop at the last bit in which we can stop, and we try not to extend. Okay, and so and theta is just bigger than or equals 0, smaller than or equals pi over 4. And now let's check this semicircle. Now I do want to go fast through this. Okay, so let's so this semicircle is just the outer is just y equals 1 minus x squared. This is in our regular Cartesian coordinates, which is basically equivalent to y squared plus x squared equals 1. So r squared equals 1, r equals 1, and this is our outer bound. Then theta goes from 0 up to pi, and that's basically our bounds. It's very simple for the semicircle. And now we do see here that we have solids. This is a solid, and we do have here also it's a cylinder. Okay, we do have our circle, and we have variable value of z, and so this is also a surface. Okay, so maybe we can find the area on the surface bounded by this region. So the volume under the surface bounded by the region x squared plus y squared equals 1. So this is the solid region in example 4. Example 5. Okay, so it's kind of a cylinder, but with a conical top. So if I can draw a side view of this, it's gonna be something like this. Okay, so it's gonna be something like this. So it's not really a cylinder, it's a cylinder, but at the top it's like a semicircle or whatever you can call this. So it's not like straight cylinder. If we say this is the side view. So it's interesting. You can find the shapes, you can find volumes of different shapes. So this is the solid region, example 5. Now this is also another example. So this is the region R in example 6. Okay, so this is one example. So here we have y equals square root of 3x, and so r sine theta equals root 3x. Yeah, so and then x is just r cosine theta. Okay, and so r cancels, so sine over cosine tan theta equals root 3. And now basically this is a function of theta. Okay, yeah, so this is a function of theta. Okay, so here first let's see this y equals 1. Y equals 1 is basically r sine theta equals 1, so r equals cosecant theta. This is our lower limit. Okay, as for the upper limit, the upper limit is just, oh, so this is a line. So we should have not considered the line, it's just considered the upper limit. The outer limit is just x squared plus y squared, so r squared equals 4 and r equals 2. Now this is the upper limit, so r is between, so bigger than cosecant theta, smaller than the 2, and the theta is just from, now we do have this, we do have the points of intersections. These can be found easily by just substituting the value of y into this function. We have x squared plus y squared equals 4 and y equals 1, so x squared plus 1 equals 4, so x squared equals 3, x equals root 3, and y is 1. So, and to find the angle, tan theta is gonna equal to tan inverse of y over x, which is 1 over root 3, and this should give me the angle, which is basically equals to pi over 6. And this is our lower theta, so pi over 6. This is our lower theta. And so we do have our lower theta, and the upper theta is the same, is gonna be pi over 3, is the same way we substitute. And now let's cover very quickly the surface area. So the surface area is given by, let's say we have a surface z equals f of xy, okay, a specific surface where xy is a point from the region D in the xy plane. So in this case, the surface area is basically given by the formula S equals the double integral fx. Now maybe this could be not very visible. Let's draw it on this. Let's write it on the side here. So S gonna equal to the double integral of D square root of fx. Okay, this is the partial derivative with respect to x of the function z, and plus y, fy, the partial derivative with respect to y, plus 1 times dA, and we said dA is just r d theta, dr d theta. Okay, and now let's say here for our example, so find the surface area of the part of the plane. So this is our plane. Okay, this is our plane that lies in the first octet. Okay, so f of x, yeah, so let's say f equals 3x plus 2y plus z minus 6. Now this is our f. Now if we want to find fy equals 2y, 2, fx equals negative or positive 3, no, positive 3. Okay, fy is positive 3, and then also we do have here, so he's saying the first octet, so find the surface area of the part of the plane that lies in the first octet. So the first octet is just the first, there are 8 octets, and the first octet is just in the x, positive y, and positive z. And so this is our first octet, and then this goes into the xy plane. So this is the region, and the line is y equals 3 over 2x. Okay, this can be found by saying the slope, so y over x, 3 over 2x, and the intersection is just with the y plus 3. So this is our line. Okay, and then basically just we substitute these values. Okay, we substitute these values into the formula, and we find the surface area of this shape. And so this is another example you can solve, but I'm gonna stop here, and I want to thank you for watching this video.